Welcome back to the Chem OG. Today we're going to take a look at van der Waals equation. And van der Waals equation is sometimes called the real gas law. Now van der Waals equation, if you take a look at it, it seems a little bit intimidating, but let's see if we can break it down. And so van der Waals equation is used to describe the behavior of non-ideal gases. So let's first take a look at what an ideal gas is. Ideal gases have individual molecules that occupy no space, which is ridiculous because the only things that occupy no space are things that don't exist. But the reason we make that assumption is because ideal gas molecules are so very tiny compared to the vast amount of space that they occupy that essentially their space that they take up is rather insignificant. Or a lot of times the technical term we use for that is that ideal gas molecules have negligible volume. And these ideal gas molecules experience zero intermolecular forces. Again, totally ridiculous assumption, but it kind of works out because relatively speaking, those ideal gas molecules don't really experience that much in terms of intermolecular forces. And even when they do collide with each other, which happens quite frequently, it's as if that collision never happened. Everyone kind of goes off in their merry way, and those collisions are what we call perfectly elastic. And so when we take a look at real gases then, real gases do the opposite of everything we just said. So real gas molecules do take up space. Their volume is not necessarily completely negligible, and they do experience intermolecular attraction. And so van der Waals equation accounts for both of those things, that the actual molecules that we have might take up space, and these real gases do experience intermolecular attraction. And so gas molecules have more freedom of movement only if there's more available space. So let's try to quantify that amount of available space that they may have. And so the amount of available space that the molecules have is going to be whatever volume the container in which they're housed, whatever volume that has, minus the volume of the molecules themselves. So if you want to think about, a confined elevator, a very small elevator, if we want to think about how much space is available in that elevator, what we would do is we would take a look at how much volume that elevator has when it's completely empty, and then we would subtract from that the volume that's taken up by people in the elevator. That would give us how much available space that elevator now has if it has 3 or 4 people in it. You take the elevator when it's completely empty, and you subtract from that the volume that the people inside the elevator are taking up. And so the volume of the molecules then is going to depend on how many molecules there are, because if there are more people in that elevator, that's a lot more space that you have to subtract, and it also depends on how big each of those molecules is. And so if we put those two factors together, right, it depends on the number and it depends on how big they are, well, that number is going to be n times b. And just as a note, ideal gases, they have a volume that is 0. So when we take a look at that available space term, we'll see that for ideal gas molecules, that volume of the molecules term amounts to 0. So let's talk about the pressure aspect, right? When we talk about ideal gases, we think of pressure, we think of volume. So we just talked about volume, let's talk about pressure. So gases exert pressure by colliding with the walls of the container. The more it is they collide with the walls of the container, the more pressure those molecules can exert. And so when we look at real gases, real gas molecules experience interaction with one another. And because those real gas molecules experience interaction with one another, they're going to exert less force on the walls of the container. And so if we want to quantify how their attraction to one another is going to affect the pressure that they exert, we need to know how strong that attraction is. And the other thing that we need to know is we need to know how closely packed the molecules are. Because if you want to think of the very real world analogy of traffic, right? When we talk about traffic congestion or road conditions, when we talk about what makes traffic happen is because there are too many cars on the road, or sometimes in certain cases is because the streets or the highways are too narrow. And so both of those things together are going to factor in how congested our molecules are. How many cars are on the road, or how many gas molecules exist, that's going to be N. And also how many lanes of traffic are allowable. So how much space can these particular car is moving. So both of those factors together are going to be something that we need to consider. So the amount of attraction, the number of moles of that particular gas that exist, and how much volume they have in which to roam around and occupy. So to summarize what we learned about volume and about pressure, here's what we have. The correction for volume is that we're going to take the volume of the container and we're going to subtract from that the volume of the molecules as a whole. And the volume of the molecules is going to depend on how many there are, and it's also going to depend on how large those molecules are. And if we take a look at the correction term for pressure, seems a bit complicated on first glance, but it's exactly what we talked about. The A term here is how attracted the molecules are to each other. And then we also spoke about N over V, right, and traffic congestion. But that term is going to be squared because how congested the molecules are is actually quite important in how much of an impact that congestion has on pressure. And so wherever we see P and V in the ideal gas law, we're going to substitute those two terms in. So here's how that's going to look like. So here's PV equals nRT, and wherever we see pressure and volume, we're going to substitute in the pressure correction term, and we're going to substitute in the volume correction term as well. And so A and B are what are called van der Waals constants, and those are particular constants that we measure based on experimentation. And A, if you want a good way to remember what each of these represent, A stands for attraction and B stands for bigness. That's not exactly why it is that they're written down as A and B. They're written down as A and B because those are the first two letters of the alphabet. But I just gave you really two good ways of being able to remember what each of these letters stands for. So let's take a look at a few example values and see if we can understand why it is that certain compounds might have certain values in sort of a relative term. And so if I take a look at the first two entries in this table, I'm taking a look at ethane and I'm taking a look at methane. So those two molecules right there. Let's take a look at the B column first. And so ethane is a larger molecule. It's got a bigger bigness term than methane does, so not too surprised by that. In terms of their A values, both of these molecules are nonpolar, but ethane experiences, because it's larger, it experiences more London dispersion forces. So that's why the A term here for methane is a good amount larger than the A term for methane. Now, if I contrast the last two entries here, methane and methanol. Well, methanol experiences hydrogen bonding, so it has a great deal more intermolecular interaction with itself than methane would with another molecule of methane. And methanol is slightly bigger than methane, and so it's got a B value that is slightly bigger. And if I compare the sizes of methanol and ethane, I find that they're very, very comparable to one another, right? As I can see from the molecular formula. But again, because methanol has greater intermolecular interaction in the form of hydrogen bonding, it's got a larger number than that of ethane. So those are some example values to take a look at and to have a little bit more of an intuitive understanding what those A terms are and what those B terms are. So hopefully you find that the van der Waals equation is really not as intimidating as it may seem at a first glance, and hopefully those terms make a little bit more sense. Thank you so much for watching today's video. Please make sure to hit the like button, and if you haven't done so yet, please support this channel by subscribing. Thanks.